All right, so this is part 2 of your AP Stat midterm review. In problem number 14, you're asked to compute the 5-number summary of a set of test scores and then construct a box and whisker plot and describe the distribution. So in this case, there's several different ways you can compute the 5-number summary. First, though, you need to enter the data into your calculator. You can do it by hand if you want, but it probably is a little bit faster just to do this on the calculator. So you want to go into your stat, lists. This is just a one variable set of data. And enter everything in. Okay, I spared you from waiting for me to enter everything in. So everything, all the data now is in my list 1. And to compute the 5-number summary, you can either go to your home screen and go to Stat Calc and use your one variable statistics, which ultimately, if you look at the other questions, you're going to have to compute the mean anyway. So I'm going to show you how to use the one variable statistics to come up with all the values you need. You're just going to type in one variable statistics and then call up list 1 or list 2 or wherever you've saved your data. And so you're given a list of values. So remember, X bar is your mean. So I know in this case that my mean is 83.714. And I'm assuming this is points. If you continue to scroll down, you'll actually see your 5-number summary. So you'll see the minimum, the quartile 1, the median, the quartile 3, and the maximum values, and you can use those values to construct your box and whisker plot. So 68 is my min. I've got 76 as my Q1. 83 is my median. 91 is my upper quartile, and my max is 98. And so when we're drawing our box and whisker plot, the middle 3 contain our box, and then we've got our whiskers on the end. If I'm describing the distribution, I would say that the distribution of test scores is symmetric. The average test score, or a typical test score, was about an 83 points. And the interquartile range, if you compute that, Q3 minus Q1, it would be 91 minus 76, which I think is 15. So you could say the spread is about 15 points on the test. Okay, so we found the mean. I've described the distribution. We also want to figure out the outliers. The easiest way to do this, actually, if you know the data set, if you go to Stat Plot and turn on one of your plots, this is also another way to come up with your 5-number summary. So turn it on and then scroll to, so if you want your 5-number summary, you would choose the second box plot option. And then just make sure that you're calling your data from the appropriate lists. I would double check to make sure you don't have any equations in y equals, and then you can just hit zoom 9. And that'll also give you the box plot. If you press trace, this is another way. You'll notice at the bottom of the screen it tells you the min, the Q1, the median, and so forth. If you want to compute the outliers, a simple way to do it would just be to use the other box plot, which is the modified box plot, and you'll actually see that it shows the outliers. So this time, whoops. If we hit zoom 9, notice that our box plot hasn't changed. I think it's pretty clear from seeing the box plot that since the interquartile range is so wide, the only time you're going to have outliers is if the whiskers are 1.5 times longer than the box. So in this case, it's pretty clear. I think that there aren't any outliers. Even when you do the modified box plot on your calculator, you can see that there aren't any outliers. If you wanted to compute this algebraically, the outlier rule basically says that if you take Q1 minus 1.5 times the interquartile range, and there are any values that are less than that, then it's an outlier. Similarly, if we take Q3 plus 1.5 times the interquartile range, and there are any values that are greater than that, then we have outliers. So if I substitute in the data, so I know that my Q1 is 76, minus 1.5 times 15, that gives me a value of 53.5. There's nothing in my data set that's lower than that, so I have no low outliers. And then if I do my upper tail, so Q3 is 91 plus 1.5 times 15, and that gives me a value of 113.5. So there's no low or high outliers in this data set. If you wanted to just kind of see what it would look like, let me just to show you what a modified box plot would look like. If I go back into my data set, and let me just change the 68 to a 4. Then if I make sure I have my modified box plot, yeah. So now if I do zoom 9, you'll definitely see the modified box plot. And if you hit trace, it'll tell you what the outlier is. It'll also give you the modified 5-number summary. Okay. The other question has to do with suppose the next test score is a 50, how will the mean be impacted by the low score? So notice that the lowest score on the test so far is only a 68. So if I add another score and it's only a 50, that means it's going to drop the mean and make it lower. Oops, wrong one. Okay, similarly, if he were to get 100% on the next test, it would likely increase his score. Maybe not that much, but it would certainly increase his score. Okay, number 15, it says what 2 parameters describe a normal distribution, and then what notation is used. So the parameters, remember those are the values that describe a population. The parameters are the mean and the standard deviation. And the way we use the notation is we usually talk about a random variable x, we say it's distributed normally, and we use Greek symbols to represent the mean and the standard deviation. And that's the notation that we would use. In number 16, you're given information about the distribution of heights of adult American men. You're told that it's normal. And you know that the mean is 69, so remember the mean of a symmetric distribution is always in the middle. And the standard deviation is 2.5. If you remember with the normal distribution, the mean is always in the middle, and then there are 3 standard deviations on either side. So you're essentially just going to add and subtract away the 2.5. So if I add 2.5, I'm going to have one standard deviation above is going to be 71.5 inches. Another standard deviation is going to be 74 inches, and then 76.5. And if we subtract, this is going to be 66.5. This is going to be 64, and this is going to be 61.5. It says to use the empirical rule to draw a normal curve on which the mean and standard deviation are correctly located. I'm also going to illustrate the empirical rule. So we know that within 1 standard deviation, 68% of the data falls under the curve. With 2 standard deviations, now we're looking at 95% of the data, or 95% of the observations. And then for 3 standard deviations, we're talking about 99.7%. And so the questions that follow, you can certainly use your calculator to determine these probabilities or the percents under the curve, or you can just use the empirical rule, which was sort of the purpose of this problem. So it says what percent of men are taller than 74 inches? So let me use the black. So taller than 74 inches then would be this area right here. And so if I'm going to find that area, I want to think about all of the values from my empirical rule. So I know that for example, from here to here is 95% of the data. So I'm basically looking at the top tail. That means that 5% of my data would fall either here or here. And so if I'm just interested in the top half, I'm going to cut that 5% in half. And so I know it's going to be 2.5% or 0.025. In letter C, it says, between what heights do the middle 95% of men fall? So I can see very clearly from the empirical rule that that is between 64 and 74 inches tall. Okay. In letter D, what percent of men are shorter than 66.5? So now I'm looking at this tail here, and notice that it kind of matches along with that 68%. So with the 68%, I know that 32% of my data is going to be on the tails beyond the 68%. And so if I'm just looking at the lower tail, I'm going to cut that 32% in half, and it should be 16%, or 0.16. And then in the last one, it says a height of 71.5 inches corresponds to what percentile? Remember, percentile means the percent at or below a value. And so basically, if I've got 71.5, I'm looking at this area here, the whole thing. And so again, that kind of corresponds to the 68%. That means I've got 32% on the tails. So if I take, I guess the easiest way to do it would actually be 1 minus 16%. And so that's going to give you 84%. Another way to think of that is we already know that this is 68, and we also found out that this percent is 16. So if you add them together, that's going to give you 84%. Number 17, it says what formula is used to standardize a normal distribution. So normally X is distributed with a mean of mu and a standard deviation of sigma. A standard normal distribution is always distributed normally with a mean of 0 and a standard deviation of 1. So to get from X to Z, we use the formula, whoops, I did it the other way around. We say that Z is equal to X minus the mean over the standard deviation. And so on your AP exam, it's going to be very important that you show all three notations. You want to make sure you write the probability in terms of X, in terms of Z, and then to actually give the probability or the proportion or the area under the curve. So in letter 18 or number 18, determine the proportion of observations from the normal distribution. You're given that the mean is 170 and the standard deviation is 30. If you want to know the proportion of observations that are less than 150, the 150 is the X. When I rewrite it, and I'll do the thing off to the side. So basically I'm looking at 150 minus 170 over 30, and that's going to be my Z score. And Z is going to end up being negative 0.667. And now we're going to put that into the calculator. I do want to show you, though, how you can avoid a rounding error. So let's just go in here. So let's go ahead and just do the formula. If I'm doing 150 minus my mean, which we said was 170, and dividing by my standard deviation of 30, that's where I got my Z-score. So now what I want to do is go to second vars. That's where all my distributions are. This is where all of the probability distributions are. So we're going to be learning about all these other probability distributions second semester. And so if we go up, remember there's three different options that relate to a normal curve. There's the PDF, which we will never use in this course. Remember, the PDF corresponds to when X actually equals something. And when you're dealing with a continuous random variable, the probability is always 0. So the only time we use normal PDF is when we're graphing a normal curve, which we really don't do in this course. So we're more concerned with the normal CDF, which is the cumulative distribution. And so anytime we're looking at a range of values, we're going to use CDF, and that's what we're doing in this case. So I'm going to choose option 2. Now that I have standardized my my random variable, I'm looking for all the values that are less than negative 0.6667. And so I can't type in negative infinity as my lower bound, so I'm just going to type in negative 99999. And then again, I want to be very careful about rounding, because if I just type in negative 0.67 or 0.667, I'm going to get a value that's slightly different. So to maintain all those decimal places, instead of typing in the value, I'm just going to hit second answer, and it'll just recall my previous answer so I don't have to deal with any rounding issues. And so the probability ends up being 0.2525. And I would encourage you to round to 4 decimal places, although I think 3 are required. Okay, for the next problem, we're looking at the probability that X is greater than 185. And so that is just going to correspond to a Z-score. That is, here's my TI. So I'm doing now 185 minus 170. divided by 30, and we get a z-score of 0.5. And so when I go to put in the probability, again, we're going to do second vars. That's where my distribution options are. I'm going to choose the normal CDF. This time I have a lower bound of 0.5, and since I'm looking at all the values that are greater than that, my max is infinity, and I can't type that in, so I type in 9999999, and I get an area of 0.3085. Okay, and then lastly, we're looking at the probability, or the proportion, I guess, of observations that fall between 162 and 174. And so 162 minus 170, fix that, divided by 30. So I have a lower value of negative 0.22222. Did I do that right? 162 minus 170. Yeah. And then for the upper bound, we're looking at 174. So 74 minus 170 divided by 30, 0.111, or 1333, sorry. Okay, so this time when I choose my CDF, my lower bound, if I just do the second answer thing, it's only going to recall the previous answer. So I'm actually going to have to substitute or type in my 2666. So I'm going to give it a bunch of decimals just because I want to be as accurate as possible. And then when I recall my upper bound, I can just use the recall button. And so this time it's 0.1582. Okay, because remember when you're rounding, you look at the next value, and since the next value is a 6, that means the 1 is going to increase to 2. Okay. Number 19 now is a application of the normal distribution. I'm not going to go through the calculator commands on this problem because I just did it, and if you need a little bit more practice, you can just rewind. So in this case, in number 19, the snack pack of potato chips is advertised to weigh 3.5 ounces. The weights are normally distributed with a mean of 3.5 ounces and a standard deviation of 0.2. For a snack pack of potato chips, determine the proportion of snack packs that weigh less than 3 ounces. So what I'm going to do is I'm going to say X would be the weight of the snack pack, and X is distributed normally with a mean of 3.5 and a standard deviation of 0.2. So when you're asked to use proper notation, that's what you should use. Make sure you define your random variable as well. So if I'm looking for the proportion of values that are less than 3, when I rewrite that in terms of z, and again I'm just subtracting the mean and dividing by the standard deviation, I get that z would have to be less than negative 2.5. And when I do that in my calculator, you should get 0.0062. In letter B, we've got the probability or the proportion of that weigh more than 3.7 ounces, and that should give you a z-score of 1, and that's 0.1587. And then in letter C, we're looking at between 3.2 and 3.6 ounces. When I rewrite that in terms of z, it's negative 1.5 and 0.5, and the area in between, now this one, you do have a lower and an upper bound here, and so that's going to be 0.1582. In letter D, it says snack pack completes periodic quality control inspections by randomly selecting a bag of chips from each batch. The company will discard the entire batch if the selected bag falls below the 10th percentile of weights. And so remember, 10th percentile, if I'm looking at my normal curve, 10th percentile is the lowest 10%. And so for what weights would the snack pack discard the batch of chips? So this is an example of when you have to actually use the inverse normal, because now you're given the area and you have to figure out the x value. So if you're given the area, we can use our calculator to come up with the z-score first. Okay, so we're going to need to use the inverse normal operation on our calculator now to find the corresponding z-score. So that's option 3. And when you're using this option on your calculator, you only are putting in the lower area. So if I was talking about like the top 10% of bags, I'd need to actually enter in the lower area of 0.9. So in this case, since I'm talking about the lowest 10%, I'm just going to type in the area, and that's going to give me the corresponding z value of negative 1.282. And now that I know z, so remember our formula, we have z is equal to x minus the mean over the standard deviation. So I know z is negative 1.282. I don't know the value of x, but I do know that the mean of this distribution is 170 and the standard deviation is 30. So to solve, I'm just going to multiply both sides by 30 and then add 170. And that's going to give me an x value of 131.553. Is that right? I did something wrong. I was using the mean and standard deviation from the previous problem. Whoops. All right, so we know that negative 1.282 is equal to x minus, I'm sorry, the mean of this distribution is 3.5, and the standard deviation is 0.2. So let's try that again. So, actually, let me get those decimals back. Okay, so actually, sorry, I'm going to multiply by 0.2 and add 3.5. There we go. That makes a lot more sense. So now we're looking at an x value of 3.244 ounces. Sorry about that. All right, in number 20, this also has to deal with a normal distribution. If we're given that the mean of a distribution is 20, and we're also told that 45% of the observations fall above 30%. So let me just kind of draw a picture. So 45 are above 30. So we're looking at this area here is 0.45, and I know that the mean is 20. Oops. But I don't know the standard deviation in this problem. So if I'm going to find it, I know that my x value in this case is equal to 30. I can figure out the z value, again, using the inverse normal distribution. Except when I enter the area, I have to enter in the lower side of this. So again, I'm going to use the inverse normal operation. And the lower area is 0.55, or 55%. And that'll give me a z value of 0.1257. And so I know my mean. I now have a value for x and for z. So again, we're just kind of plugging this into our formula. So my z is 0.1257. X is 30. My mean is 20. And my standard deviation is unknown. So the way we're going to solve is just by multiplying by the standard deviation and dividing by 0.1257. So the standard deviation is going to be 30 minus 20 over 0.1257. And that should actually just give you a standard deviation of 79.579, which is completely unreasonable for this problem. If we have a mean of 20, to have a standard deviation of almost 80, it doesn't sound right. But I think that's just a mistake with how this problem was set up. Math is correct. All right, number 21 is really just the last problem that you were asked to complete. Everything else is just a reminder of things to review. So in number 21, it says the scatter plot below shows the relationship between lean body mass and resting metabolic rate for 12 women. Identify the explanatory and response. Remember, your explanatory variable should always be on the x-axis, and your response variable should always be on the y-axis. So in this case, the explanatory variable is body mass, and the response is metabolic rate. It says to describe the association between the variables in terms of the strength, direction, and the form. I think that this looks like it's a moderately strong association. It's positive and linear, but you do want to make sure that you're using the context of the problem. So you might want to say, the relationship indicates that as the body mass increases, the net or the metabolic rate increases as well. It appears to be linear, so it's increasing at a constant rate. It's a moderately strong association. In letter C, it's actually asking you to estimate the correlation coefficient. I think we can eliminate all the negatives. It certainly isn't zero. It's not a perfect correlation, and it's moderately strong. So I would actually lean towards the 0.7 as my correlation coefficient as opposed to the 0.5. And then in the last question, it says to use the correlation coefficient to determine the coefficient of determination. Remember, that's r squared. So if you know that r is 0.7, then r squared is going to be 0.49. And so then you're asked to interpret what that value means with respect to the problem. It's important that you understand this. This tells us that 49% of the variation in the y variable, which in this case is metabolic rate, and that can be explained by a linear relationship on the body mass. Okay. In problems 22, it's not really asking you to do anything except to just review your notes for graphing a model along with the original scatter plot, examining goodness of fit, comparing your R and your R squared values with each model, being able to construct a residual plot. So make sure that you remember a residual is always the actual minus the predicted. And so if you're doing a residual plot, in your L1 is where you usually have your X's, and L2 is where your Y's are. So in L3, you want to use your equation. So do your Y1 and then evaluate that at list 1, and that'll give you your predicted Y values, because you're basically going to evaluate your function at all of the values of X. So this is your actual Y. And then list 3 would be your predicted Y. Your residuals then you would find just by taking L2 minus L3. And then the residual plot is basically when you use your original X's in L1, but then compare them to your residuals in L4. And then you'd want to zoom 9 them. And remember, we never want to see a pattern in a residual plot. If you see any kind of pattern, that's an indication that a nonlinear model is a better fit. If you see any points that are like really far away, so for example, that would be like an ideal residual plot. Anything where you see a pattern indicates that a nonlinear model would be more appropriate. If you see anything where there's like a cluster of points, then that's an indication that we have influential observations, and so the model may or may not be appropriate depending on the rest of the data. The other thing you also have to remember how to do is to linearize the data. And so when you're linearizing data, remember that, so if you have your original X's in list 1 and your original Y's in list 2, list 3 you would basically take the natural log of list 1, and that would be your log of X. And in list 4 you'd want to take the natural log of list 2, and that would give you your log of Y. And then what you'd want to do is plot. And look at the graphs. So if you plot, for example, X versus the natural log of Y, and so that would be the same as list 1 versus list 4. If that's linear, then you're going to use exponential regression on the data, on the original data, on X versus Y. Okay? If the plot of, let's say, the natural log of X versus Y, okay, and that would be basically your list 3 versus list 2. If that's linear, then you're going to use natural log regression. And again, you're going to use it on the original values of X versus Y. If the natural log of X versus the natural log of Y, and that's going to be your list 3 versus list 4, think pow pow, that is your use power function or power regression. Okay, on X and Y again. Now, obviously, if when you plot x versus y, if it's a straight line, then you're not even going to consider a nonlinear model. You'll just graph it with a straight line and do linear regression. So the only time you'd actually do this linearization technique is if it's obvious to you that the original data is nonlinear. And because the linearization techniques actually, that's how your calculator computes the exponential, log, and power regression equations, it actually enables you to compare the R squared and the R values of those equations that you get. And then finally, for the probability unit, I've already shown you what formulas are going to be available to you on the test, so let's just review what these rules are. The probability of A complement is just 1 minus the probability of A. In the probability of A or B, this is the general rule. So we're looking at the probability of A plus the probability of B minus the probability of both A and B. Remember, with the or, you're adding. With the and, you're multiplying. So please make sure that you have that in order. If the events are disjoint, okay, so actually that comes down here. For disjoint events, that means there's no overlap. Disjoint and mutually exclusive mean the same thing. There's no overlap. The probability of A and B is 0. So that would change my addition formula to be the probability of A or B is simply the probability of A plus the probability of B minus 0, which I don't really need to put there. For independent events, the probability of A and B is simply the probability of A times the probability of B. I have found that a lot of students are using this formula regardless of whether the events are independent. The events must be independent to multiply the probability of A times the probability of B. Going back to our addition rule, though, if I know that my events are independent, then that is going to transform my addition rule to be the probability of A plus the probability of B minus the probability of A and B, but if they're independent, that's just going to be the probability of A times the probability of B. So you really do have to check for independence to know which formula to use. And this is something you should be able to reconstruct. I don't expect you to memorize like 16 different formulas. With conditional events, so if you have the probability of A given B, then you're looking for the probability of A times the probability of B given that A happened. And this formula you would use regardless of independence. If the events are disjoint, oh, I'm sorry, I wrote the wrong formula. I actually just did the multiplication rule. I'm sorry. I skipped it. I meant to do this. So with A and B, it's going to be the probability. It's going to be the probability of A times the probability of B given A. I apologize, I wrote it in the wrong spot. That is your general multiplication rule. And so if the events are independent, then it's not going to matter. The probability of A or B given A is just going to be the probability of B. So if I were just to rearrange this formula, the probability of A given B is the probability of both A and B divided by the probability of B. If they're disjoint, the probability of A and B is just 0, and so the probability of A given B is 0. And if they're independent, then it doesn't matter if B happens, the probability of A won't change. Okay, and I think that's about it. If you have any other questions, obviously you can email me over the weekend. You can ask me at the beginning of class. But hopefully I've covered everything that's on the midterm, and hopefully you guys are going to feel really good about it and do really well. Good luck.